Hello, everyone. Welcome to Space Club. I'm Danny Bednar, part-time assistant professor in the Department of Geography at Western University, where I teach about space exploration. And with me for Space Club today, as always, is Dr. Phil Stuke, professor emeritus, also from Western University, and Tanya Harrison, Dr. Tanya Harrison, Mars scientist and otherwise person.
I'm just going to change that to my LinkedIn description now.
I'm taking that as a compliment, I think.
Yeah.
I think so. In these troubled times, it's always good to be reminded of your personhood.
Sufficiently human.
Yeah. So, as you can see, today we are talking about Mars sample return. Actually, just before we started recording, we were talking about some of the historical discussion of this. And Phil, I think you're going to jump into that pretty soon as well. But spoiler alert, we have not done Mars sample return for those totally new to the subject. So this is all right now in the realm of possibility and hope. So Phil's going to give us a good rundown of how close we are and what kind of ideas there are to do this. Before we get going, anything, Tanya, that you want to throw in on Mars sample return?
I was just rereading the Rocket Lab proposals for what they want to do if we want to dig into the industry side of things in this discussion.
That would be very good. Yeah, very good.
Okay. Yeah, we can get there. Or do you want to do that right now, or you want to get there? Maybe it might come up naturally. Yeah.
Yeah, I feel like it's better, makes more sense later.
Yeah. And I was just reading my handy International Atlas of Mars Exploration to get a sense of some past ones, because I was trying to remember. And I don't want to take too much of your time, Phil, but I know, so post-Viking, there's a ton of discussion in the late 70s, early 80s about Viking 3, about Viking rover. Obviously, that never ends up happening in the 1980s, but built into that infrastructure were ideas for sample return in the 80s. Probably would have been completed by the mid-80s, late 80s. And that was work done, again, in the immediate aftermath of the Viking program, while it was still, I guess, alive. And then into the late 80s, we get the Mars rover sample return kind of working groups at NASA, which was another big focus. Again, all of this is in Phil's book. Mm-hmm. They're pretty standard, but pretty advanced mission design, architecture, 11 proposed sites. One of them used to kind of demonstrate the mission architecture, which is East Mangallo Vallis. Mm-hmm. I don't know if either you know where that is off the top of your head. I obviously do not. But they got traverse maps, all that, and something that'll be of interest is this is 87 through 89 over at NASA with help from USGS, who used to be really involved with Mars stuff. And the mission architecture was NASA would do the launch, rover, lander, and orbiter, and the orbiter would be for comms. And then an international partner would do the lander and ascent vehicle, and then the return craft. So that's an idea that's not too far off from where we were just a few years ago, and where we may still be. So, as is often the case in space exploration, there's piles and piles of reports on these things that if you want to dig in, and someone like Phil has, it's not a new idea. People have written about it and had a lot of meetings on it in the past, but we'll see where we are today. Phil, anything that rushes to your memory from writing these books and looking through all those reports?
Not really. I just think that the thing that is that now we would regard as essential is having all the wonderful remote sensing data sets that we've got right now for composition and topography and high resolution imaging and so on. And when they were planning these things just after Viking, they didn't really have any of that. We had quite rudimentary imaging coverage of the planet and not very good topography and all that sort of thing. Not much composition information. So they couldn't actually have chosen really interesting sites in those days. And it might be a good thing that they didn't go ahead and do it. Now we have fantastic data sets to help to plan these kinds of missions. And we can just do it so much better now.
Yeah, they were essentially working off of photographs and very rudimentary spectral analysis, I guess.
Well, there wasn't really, there was hardly anything. Viking took 3-color images, not what we would call multispectral imaging today.
Mhm.
So they could make a pretty color picture, but you weren't learning very much about composition from it.
Yeah.
They just didn't have the compositional data sets, or the very high resolution imaging for planning things like where a rover could drive. So it just wasn't possible back then. Whatever they did would have been a very different kind of mission than what we would plan today.
Okay, well, let's find out what we will plan today, or what we have planned today, if I can move this ahead.
Okay. As we've just kind of indicated, people have been talking about all this stuff for quite a long time. You want to bring back some rocks and soil, and I always like to remind people that you'd bring back a bit of atmosphere as well, because that would be an interesting thing to sample. So people have been thinking about it, and why would you want to do it? Because it's going to be tremendously expensive, and the reason, of course, is that we can do much better analysis here in a lab than we could do on Mars. And we have wonderful, wonderful instruments on Mars right now, on the big rovers, especially on Perseverance, wonderful instruments. But even so, you could do much more in a lab on Earth. You just have every instrument you could, that we actually have today, not just the few that have been boiled down to stick onto a rover. And another reason for it is that if you can bring a sample back and have it here on Earth, well, you can put some of it aside and wait 20 years, 30 years, and then analyze it again. You've still got the sample. You can analyze it again with even more advanced instruments from 20 or 30 years into the future. And we've just been doing that with the moon. We've just had 50-year-old samples from Apollo 17 that just sat in storage for 50 years, not even opening the containers, so that they would be pristine and ready to analyze with much more up-to-date instruments. And we've just been doing that over the last couple of years. So this would again be possible with Mars samples. You bring them back and you've got all our wonderful instruments, and we can put some aside and save it for analysis 20, 30, 40 years into the future with even more amazing instruments. So it would be a great thing to get those samples back to Earth if we can do it.
Yeah, and I think sometimes you don't need much of a sample to work with necessarily. Like obviously you want as much as possible, but like a single researcher can do a lot, can do an entire PhD project, can have multiple PhD students graduate on a single grain or a few grains of, and we saw that at Western where we were, of the Apollo samples, right? Like I saw Patrick's samples. They were not huge. They're tiny, tiny fraction of what we got a ton from the moon. But that's the other thing to remember is even if we get, we'll talk about the amounts later, 1,000 grams or something, that's a lot. You don't even necessarily need a gram to do a lot of work.
Yep, right. Yeah, that's true. So so let's go on to the next slide. So so I want to talk about two different ways that you could do this. I think we skipped a slide there, did we? Did we just skip a slide? Oh no, I guess we didn't. All right, never mind. Okay, so there are two different ways that you can think about doing this. One is that you just fly a spacecraft to Mars and scoop up a sample and bring it back. And basically, when you're there, you don't have a lot of time to drive all over the place and select really good samples. You land somewhere and you scoop what is right beside your spacecraft, and off you go with it back to Earth. And this was really the first way people started thinking about these things. And it works really well if you have a big uniform target. This sample of a geological map here from the US Geological Survey indicates some areas that people have interpreted as different kinds of rock, big areas of lava flows, big sedimentary areas up in the north there. You might have an area that's 1,000 kilometers across and pretty much all the same kind of rock. So it doesn't really matter exactly where you land. You could be 10 kilometers off your target point and you're still in that same stuff. And you land there and you scoop it up and you bring it back. And if you've chosen the area carefully, then you're getting a really valuable sample anyway. So you bring it back and you've got something that will date that particular kind of surface material. Let's say the lava flows. Let's go to the next slide. There's a close-up of one of these areas. This is an area called Hesperia Planum, and it gives its name to the entire middle section of Martian history, the Hesperian period in Mars history. There was lots of lava flows erupting onto the surface, and this is one of them. But we're not really sure exactly where it is in terms of its age. And if you could just land on that lava flow, which is, 1,000 kilometers across or more, just get in there, scoop some of it up, a few little rocks, some soil. You get the chance to get a date for that particular lava flow, which is one of a widespread sequence of lava flows across the planet. And now you've kind of tied down part of the geological history of Mars, much better than we can attempt it without a sample. So that's one way to do it. It's just you take one spacecraft, you drop it on the surface, you scoop up the sample. You might drill a little bit, to try to get deeper into the soil. Scoop it up, drill it, whatever, package it up, and bring it back. So this is one way to do it, but now let's look at another way, and that is a much more sophisticated approach where you collect a carefully selected set of samples from a really interesting area. And I say here multiple missions because you might land and collect the sample and then something comes in later on to pick it up and bring it back. It might be more than one mission on its own. But the important thing really is you're carefully selecting these really interesting samples from an area that is complicated and interesting and has all sorts of different kinds of material in it and different stories to tell about the evolution of the surface and its climate and maybe if there was anything living in it. So you choose very carefully where you want to go based on all these great data sets I was talking about before. We've got the composition. The next slide shows one of these compositional data sets, images from the CRISM instrument, which uses infrared spectra to tell us something about the composition of the surface. And you look at this, and the different colors represent different kinds of material. Down there in the lower right, there's some yellow stuff and some sort of pinker stuff, different kinds of material. And then in the middle, some purple stuff. And on the left, there's some green. They're different kinds of material, and we get an estimate of what they're made of. And so you can carefully select where you get the samples so that you're sampling all this different stuff. Now, this particular place is Jezero Crater, where the Perseverance rover is, and it landed in the lower right corner, and it sampled some of that pinker material and yellow material. So we've got those samples, and then it drove up onto the delta, the area in the middle, which looks like a delta it was built out into a lake at some point. And they collected samples from there, and they moved into the green stuff, which has carbonate minerals in it. And they've collected some of that. And now they're up on the hills on the left-hand side and looking for even more different kinds of material. So you choose a really good place with a lot of stories to tell about the geology of Mars and the history of Mars. And then you go in there and you collect them like that. Very high value samples, very carefully selected. And you get that set of samples and then you store them on the surface for something to come and pick them up later on. So, yeah. Now, we have done things like this before, right? We haven't done it on Mars, but we've done it on the moon. And both kinds of sampling have been done there. The Apollo missions did my sort of type 2 sampling, the much more sophisticated version of it. The astronauts went to interesting places, especially in the later missions. Interesting places where there were multiple different kinds of material to sample. That picture, there is Apollo 17. And there they were able to sample volcanic materials on the floor of a valley, rocks from the mountains on each side of the valley, a landslide deposit, and here there is a little crater that had dug through the landslide and brought up darker material from underneath. They thought it might have been a little volcanic vent, and they were wrong about that. It was just an ordinary impact crater that had dug through the landslide deposit and brought up some dark material to make a little dark patch on top of the landslide. But we didn't know that until they went there to collect it. So anyway, all sorts of different kinds of material, and they were well trained. All of the astronauts had geology training, and one of them on this mission was a geologist, and they also had the benefit of scientists, teams of scientists on Earth who had worked for several years figuring out where you would go, choosing the best places, figuring out where you would collect the samples, the whole thing very carefully designed. So that was that sort of type 2 sampling. And you can set that against my first kind of sampling that I mentioned, which was done first by the Soviet Union with 3 landers called Luna 16, 20, and 24. They just dropped down on the surface, scooped something up, and brought it back. And since then, China has done the same thing twice with Chang'e 5 and Chang'e 6. Now, the way I'm describing this, it kind of makes it sound like these simple sampling missions aren't as good as the more sophisticated ones. But I don't really want to give that impression, because I don't think anybody doubts today that the Chang'e 5 and 6 samples are profoundly interesting and important. And that's partly because they were very carefully selected based on the new things that we know about the moon. Things that they didn't know at the time of Apollo. So they've chosen these very carefully. They've chosen these places, and also, as Danny mentioned, you only need a few tiny little grains to do really interesting work. So if Chang'e 5, Chang'e 6, if they scoop up some soil just from the surface in front of them, there are hundreds of little grains in there, thousands maybe, and each one has its own story to tell. They've been thrown in from different places, different impacts around there. They've had different histories, different stuff has happened to them. And you can really do a lot with that. So both kinds of sampling are actually quite worthwhile. As I say, we do have this history from the moon to base what we think about Mars on. So now let's look ahead to the next slide. So back to Mars. So here's the plan, basically. First, you collect samples. Second, you cache them or store them on the surface of Mars. And then when the time, the money, the technology permits, you go in and collect them and bring them back to Earth. And what we're looking at here is a picture of a little place called Three Forks, where the Perseverance rover has left a cache of some of its samples. There are 10 different sample tubes there. They each have a name. Each one is a different kind of rock. So we've got rocks here from several of those different kinds of places that we were just looking at in that colored image, the chrism image. They've been selected. They've been documented. They've been analyzed on Mars before they're collected. Now they're stored for us. So then, of course, you have to figure out what you can do. So this is the cache on the surface. Let's look at the next slide there. And there's one of those sample tubes. It's not very big. It's just like a little sort of a pencil-sized thing. a little cylinder of rock inside it, carefully sealed at the end so it won't be contaminated. It's been drilled out of rock. They've had one or two cases where they drill something and it's so sort of weak and poorly cemented together that it just crumbles and you don't actually get a proper sample left in the tube. But in most cases, they've been able to collect what they need. So that's one of the samples. It's a nice little tube sitting on the surface. We know exactly where they are, like to within the centimeters. We know exactly where each tube is. So something's going to be able to come in later on and land nearby and pick up those tubes that will be just sitting there waiting, even if the wind has blown a bit of sand over them. And I don't really anticipate very much of that. But even if that had happened, we know where they are, and it would be easy enough to track them down. So you just have to collect them, and that's the tricky bit. So now let's think about this. Collect and return to Earth. It's so easy to say that, and so difficult to make it happen. This is the tricky bit. So let's go to the next picture here. Here's one kind of version of this where you have multiple spacecraft. The Perseverance rover in the lower left, that's already there. That's already collecting samples. It's collected that one set of samples and already left them on the surface. But it's got a duplicate set, a set of copies of those still in it, and all the new stuff that it's been collecting since. And it's really this the remaining stuff that is in the rover now and that it still has to collect. That's what we really want to bring back because it's a much better set of samples. But if something goes wrong with Perseverance and we're unable to get those samples out of it, then there's this already a baseline set of things on the surface for us to pick up. So Perseverance is already there. But we're going to have something that will land nearby. So there's a sample return lander. Then we got to have something that will take that sample back up to orbit, the Mars Ascent Vehicle. And then somewhere up there in orbit, an Earth return spacecraft, which in this case is indicated as coming from the European Space Agency, and that's one possibility. And that's there. The Mars Ascent Vehicle will go up to that, deliver the samples to it, and it will come back to Earth. So there's our strategy. That's how we're going to do it. Of course, it's still not quite as straightforward as that. What about that little bit where the samples have to get from the rover into the sample return lander and into the Mars Ascent Vehicle? How do we do that? One idea that people have talked about for quite a long time is that basically Perseverance would take its samples and drop them on the surface, just like the other set. And a little rover would come across from the sample return lander and pick them up and deliver them to the return vehicle. So it might be a little rover. Sometimes it's called a fetch rover because it's going to land and then fetch the samples back to the return vehicle. So that's a possibility. More recently, with the success of a lovely little helicopter called Ingenuity that was with Perseverance earlier, not working right now anymore, but it had a really successful mission. So people got all excited about that. So the idea that you might have one or two little helicopters doing this job of picking up the tubes and returning to the lander, that came along too. So it might be a rover, it might be a helicopter, or conceivably Perseverance could drive right up to the landed vehicle and deliver the samples to it directly without something else to pick them up. So you've got different ways to do this, and people are looking at the different approaches that might be attempted. But we don't know exactly how that will work yet. Although there's some proposals, which I think Tanya will tell us something more about. Okay, so now let's go on to the next slide here. So as I say, NASA had been developing these plans, but it just became really expensive. And so basically the whole process has been postponed a bit while people reevaluate how this could be done. And it is a it is going to be a complicated thing, and there's no denying it will be an expensive thing to do. So whether that is what will happen or not, I don't know. But here we are in 2025. Even if NASA made the decision next week on exactly how they were going to do this, they would be very unlikely to get that off the ground by about 2028 and get the sample back in the early 30s. Chances are they won't get off the ground until 2030, and you'll be into the 2033 or 4 before you get the samples back. So this could be quite a long-term thing that we're talking about here. Meanwhile, there's another player on the stage. So let's have a look at this is my last slide here. And this is China. China has been doing some pretty spectacular things in space. Its sample return missions to the moon have been spectacularly successful, and they are very sophisticated. And it's already had a successful orbiter and lander and rover on Mars, so it knows how to land on Mars, and it's got that experience. And now they're planning a mission which we expect to be launched in 2028. It will be one of these, what I've called a Type 1 sampling mission, where you land and you scoop up some stuff from right where you are and bring it back. They'll choose a really good place. It'll be carefully chosen. It will be scientifically very valuable, no doubt about that. And if you get a whole mixture of different kinds of rock, you're learning all kinds of interesting stuff from it. So it will be good. It will be a good mission. And if it launches in 2028, they will have their sample back almost certainly, I would say, before NASA gets a chance to do it. So there's some sort of considerable boasting value in that, that they'll get the first samples back, even though the NASA ones might be more sophisticated and carefully chosen and so on from a different kind of site. But we've got lots of things to think about now as we look ahead to what's really going to happen with sample return. Okay, so that's my summary.
I know this image is from I guess an online news site, but it really looks like you had like a spy cam.
Yeah.
It looks like how NASA learned about Lunicott or something.
Yeah.
Tanya, you wanted to talk about some of the commercial studies you've been reading?
Yeah, Rocket Lab actually has a really beautiful website to just scroll through. But I guess before I share my screen, basically, to kind of go off of what Phil was saying, that this is going to be really expensive. The budget for MSR, Mars Temperature, has ballooned to $11 billion before even settling on what the architecture was going to be. And so obviously this was just getting wildly out of control. And unfortunately, it's had a lot of ripple effects, like partly leading to some of the layoffs at the Jet Propulsion Laboratory. And the solutions that NASA was looking at were still, even trying to backtrack from there for some of these other options, upwards of $6 billion, and probably upwards of $7 billion, depending on which constellation of things you picked. And so they had put out some feelers to the commercial sector for the launch side of things specifically, but then Rocket Lab kind of pulled something untraditional, and they just said, hey, here's a proposal for you if we take over the whole thing, and we can do it for under $4 billion, including some stuff that you didn't even ask for. So let me share my screen here. So Rocket Lab is interesting in that they're one of the companies that actually has a CEO that seems interested in planetary science. He's been investigating doing a Venus mission for a little while that they've gotten a lot more press for, I think, than their Mars interests. But they did have some involvement with Perseverance and Ingenuity. They worked on the Escapade mission. So they've got a little bit of credibility when it comes to Mars. And they proposed this model where, let's get down to the sections here. Basically, they want to build the Mars Ascent Vehicle, the Earth Return Orbiter, the Entry, Descent, and Landing System, the Retrieval Vehicle, and the Earth Entry System, but also this Mars Telecommunications Orbiter, which is something that NASA has expressed a need for since at least 2022, I think it was. I got invited to a kind of Mars exploration program industry day where they invited, I'd say maybe 40-ish or so people from the space industry to come in, and they presented to us, these are the things that we need help with because we're spending so much money on Mars sample return. We don't actually have any budget or plan for replacing some of the critical infrastructure that we have, like the comms relays for landed assets that are right now all going through relatively old to very old technology. When we look at these orbiters, MAVEN, which has been at Mars since 2014, Mars Reconnaissance Orbiter, which has been at Mars since 2006, 2007. So these are aging assets. We can't necessarily assume that they're going to be working forever. And so the plan here was that they proposed that they were going to send this MTO, Mars Telecommunications Orbiter, not just to help with this particular mission, but to leave in orbit and help with future missions. So for under $4 billion, they're proposing this critical infrastructure on top of getting those samples back. Then they've planned 3 dedicated launches to provide the orbital and surface assets to Mars to go with all of this. A little entry and descent system to deliver a sample and retriever lander and Mars ascent vehicle to the surface of Mars. And there's the little lander with the ascent vehicle. Capture all the samples, bring it back up. Rendezvous with an Earth return orbiter to capture the samples, which is very similar to kind of one of the original notions of doing Mars sample return, delivering the samples to something in orbit, and then that thing brings it back to Earth. And then you have your Earth entry system where it would jettison out a little capsule, kind of like we've done sample returns before, and then landing in the Utah desert, which again, we've done that before with previous missions from stuff way farther away than Mars, like comets. So we know how to do this. And they really highlighted a bunch of the stuff they've already done on Mars, which again, like I said, I don't think they've promoted very broadly beyond, actually maybe not even in the space industry, but they've worked on a bunch of different things related to Mars. Mostly things like solar power assets. Like, our solar panels provided power for the Perseverance rover's cruise stage and again on the Mars Ingenuity helicopter. And the other non-traditional thing that they did here is that they proposed this to NASA as a firm fixed price contract. So they're like, we guarantee you that we will give this to you at that sub $4 billion price point, regardless of how much it actually ends up costing. Now, we've seen that before, sort of, in things coming from the commercial space sector where you've got like a lot of venture capitalist backing, and so it kind of makes stuff look cheaper than it actually is because you're paying with a bunch of money that somebody had sitting on the ground. So curious to see kind of in the long run, if they do end up doing this, is it something where they can actually build all of this for the price tag they're proposing, or is it something where Peter Beck, the CEO of Rocket Lab, is going to have to shell out a bunch of his own money to make this happen? But he does seem genuinely interested in trying to work on this kind of stuff. He actually just did, I guess, the most recent at the time of us recording this episode of the Planetary Radio podcast that the Planetary Society puts out. I think every month they do a space policy edition, and Casey Dreyer, who hosts that, interviewed Peter Beck and Richard French, who's the head of business development for Rocket Lab, kind of going into the process behind putting this together and why they decided to do it. So if you're interested in hearing more, I found it to be an interesting interview.
So it's noticeably the exact infrastructure from the late 80s Mars rover sample return workshops, with comms orbiter as well, which is interesting. And yeah, I mean, more power to them if they can get it done for $4 billion. Sounds good. Yeah, that'd be interesting.
Yeah.
Their proposal was, let's see.
Do they have well, you look at that too, do they have a landing site, or just that would be up to NASA, I guess?
Yeah, they didn't pick a specific landing site, and they... Oh, no, they didn't pick a specific landing site, but they want to collect the samples from Perseverance. And they're proposing that with their system, they could have those samples back at Earth by 2035.
And they've got their own launch system?
Yeah. They basically proposed a fully integrated end-to-end solution.
Okay, so I've got a bunch of random thoughts and questions for both of you from the last hour. They jump around, but so one of the things I wanted to mention, because Tanya, I don't think you joined, but before we were recording, I was telling Phil I just finished my Apollo video for my course and spent 3 weeks deep in Apollo again, which I hadn't done since the book. But when I was looking into like, oh, what science can I mention was done as a result of Apollo, and a big thing was again constraining the age of the moon, not just from the sample sites, but globally in the lunar sense, because once you've dated, in this case, 6 sites using whatever chemical dating processes you want, you can then either compare crater counts or other surface features to get a global idea, right? And this is one of the things that came from the Apollo samples. For Mars, we have assets on the ground. We've touched Mars, which we hadn't touched the moon pre-Apollo. But is there still some like constraining that could be aided by a Mars sample?
Absolutely. We don't have any definitive dates from Mars. Everything is kind of based on the lunar samples and using that combined with looking at like crater density on the moon and then kind of projecting that onto Mars. So there's a lot of assumptions there. And I think what we've learned, especially over the missions that we've sent since the turn of the millennium, like Mars is way more complicated than we thought it was in, the Viking era and even in the 90s. And so it wouldn't surprise me that if we got these samples back and, within the first few analyses, it turns out that a lot of our assumptions about Mars and the dates are actually wrong.
Yeah, it could easily happen. I mean, there are lots of assumptions, as you say. You could say Mars is closer to the asteroid belt, so maybe it gets hit more often. So there'd be more craters in a given period of time. Or you could say there's a bit of an atmosphere, there's some erosion going on. Maybe it's removing craters more than you would expect. And we don't know how these things would balance out. So there are all sorts of uncertainties about those ages just based on crater counting. So yeah, there's going to be a lot to learn from those first samples.
Okay, so something else I wanted to ask. It's more of a, is this a stupid idea question? Say you're on Mars, and we've seen this, I think. I don't remember which rover, but we've seen a meteorite on the surface of Mars. Does that meteorite have any scientific value? I mean, we get meteorites too, so we could presume, arguably, that what's a Mars meteorite versus a meteorite we get. But conceivably, would that be of interest?
Well, I guess I would say it's interesting, but if you're looking at a little place on Mars, and over there's a meteorite, and over here there's a chunk of volcanic rock, I think the volcanic rock is more interesting than the meteorite.
Yeah, I mean, it got to the point where like Opportunity and Spirit were driving by so many meteorites, they just stopped analyzing them. They might snap a picture from a ways away, but they're like, yeah, we've got them on Earth. We can analyze them here. So it doesn't make a ton of sense to analyze everyone we come across on Mars because they're all over the place.
Yeah, it's a safe assumption that the meteorites hitting Mars are the very similar ones hitting us. So they've just gone through a slightly different process recently, but
yeah, the exception would be if we found meteorites in the Earth that are from Mars, right? If we theoretically found an Earth meteorite on the surface of Mars, that could be amazing. But
that would be interesting. Yeah, that's right.
That would, yeah.
It's a little harder well-wise, but like theoretically it could happen.
Yeah. And I did want to mention, we have in theory, well, not in theory, we have in practice samples of Mars on Earth. They are in the form of meteorites that have, for some reason or another, been ejected off of Mars by a large impact, and they float through space for however long, and they land on Earth. And they're not great samples in a scientific sense because they've gone through our atmosphere and been burnt up. They've sat on our surface and been infiltrated by water and all sorts of chemicals. But there's still pieces of Mars. And Tanya, I'm sure you've talked about this in your various talks. But so we have things we think are from Mars, or we can argue pretty certainly we think are from Mars. But as I said earlier, of course, this whole episode is about how we have not taken things directly from Mars and kept them pristine.
Mm-hmm.
One of the big issues. Oh, sorry, Tanya, you should.
Well, it's that we don't know where the meteorites came from on Mars.
Yeah, that's exactly what I was going to say. Yeah, that's right. Yeah, it's fine to say it comes from Mars, but is it from an old lava flow, a young lava flow? You know, where did it really come from? And people have tried to narrow it down a little bit, but you know, it's not really easy.
Yeah, they make like overly broad, sweeping assumptions sometimes, and every once in a while, I kind of have to laugh because it's like, okay, you're doing a really important analysis, but at the same time, it feels like you're taking one rock and trying to extrapolate the whole geologic history of Mars in some cases. And you would never just take a random rock that you picked up somewhere on the Earth with no idea of where it came from and be like, tell me the history of Earth from this single rock. So the meteorites are important, but I think sometimes we try to ascribe like too much to them because we just don't have any context.
No.
People need PhDs, Tanya. We got to study something.
I apologize to my friends who study meteorites.
Yeah, let's not anger the meteoritics community. Okay, that's that. So Phil, in hindsight, at the time, this would have been, oh, we'll be back. In hindsight, Apollo, with their lunar rover especially, maybe could have cached some samples. Actually, would have been potentially quite helpful. This just dawned on me. Your face seems quizzical, but bear with me.
My face is always quizzical.
They've got a rover. They've got access to a few dozen kilometers at a time of distance. They can only bring so much back on the ascent stage of the LEM. Of course, we probably assumed in 1972 we'd be back a whole bunch, no big deal. But now, if we had a nice cache of samples the astronauts had put together for us, and we could just grab it with the lander, that would be great. Of course, hindsight's 2020, but it just crossed my mind while you were presenting. I haven't given it a ton of thought.
Okay, well, let me just shoot you down there, Danny. Because the problem is that they would be coming from places that we already know quite a lot about. And the thing is that there are so many places on the moon that we haven't been to, some of which weren't even recognized at the time. All sorts of interesting things, compositional anomalies like Compton-Belkovich and the lunar swirls that we understand better now than we did before, and the irregular Mare patches. These funny there are all sorts of little things that weren't sampled, and it would be much more interesting to go to them than to just, let's say, go back to Apollo 15 and pick up a few extra samples that they didn't bring back. So I don't think it's actually very useful to do it.
It'd be more the same, but more.
Yeah. Okay. Okay. Fair enough.
Yeah. If their mission was drive as far that way, grab something, drive as far that way, grab something, and knowing that they couldn't bring it all back, but they could cache it, I'm just, I don't know. I'm just freeballing here.
Well,
you don't seem
okay,
convinced.
Whatever.
I'd
rather go to new places.
Yeah. For anyone wondering, one of the great challenges of exploring Mars is getting off the surface if we want to bring back samples. If you were paying attention, you noticed, of course, we got off the surface of the moon, both with people and with robots in the 70s and recently. Quick reminder, if you are watching this and you're not a planetary scientist or astronomer, it's much easier to get off the moon because the gravity is much less and there's no atmosphere holding you back. So one of the ever-present challenges for Mars exploration is it's easy to get, well, it's not easy to get down, but we've gotten down. We have never gotten back up, and that remains to be seen.
Yeah, now, when the Soviet Union collected samples in the 70s from the moon and brought them back, they had a really ingenious way of getting them back to Earth. It didn't really require any extra help after they got off the surface. And that was that they launched off the surface in a certain direction that just meant that they were traveling. You come off the surface and you're kind of still traveling in the moon's orbit, but because you're pushing away like this, you're going a little bit slower than the moon and you just fall in towards the Earth. And that does constrain where you can take off from the moon. So it really tightly constrained where they could do this. But it was a very simple way of getting up. All they had to do was get off the surface, push themselves away from the moon a little bit more than escape velocity in the right direction, kind of backwards along the orbit. So that's slowing them down relative to the moon, and they fall in towards the Earth. And that's what they did. But there's no way that could ever work.
Not an option. Yeah, not an option for Mars.
It's not.
Something else will grab you before the Earth, probably.
Yeah.
So if we're keeping score in terms of what bodies, I won't say planetary bodies, what bodies we do have samples of that are not meteorites, we've got, of course, the moon in a good abundance. Wild 2, a comet, which we have samples of its tail. Atakawa and Ryugu, the 2 Japanese sample return missions from asteroids, and Bennu, the asteroid sampled by NASA, OSIRIS-REx. So that's where we're at. We've got the moon, a comet tail, and 3 asteroids.
Yeah, that's right.
So we're still looking. Mars is the most reasonable next one. I don't know. Venus atmospheric sample somehow seems like a challenge.
I have talked about that. In principle, you could collect an atmospheric sample from quite a few places just by kind of diving in, like sort of a grazing flight through the atmosphere and then the other side, but scooping up a bit of atmosphere. And I mean, it might be nice to have the atmosphere, but you might get some dust and stuff as well. And so certain people have talked about doing that. You fly through the atmosphere of Mars, maybe 100 kilometers above the surface, but you get some atmosphere and you might get some dust, and that would be a sample. And that would be like sampling the comet.
Yeah.
Looking back, whether that could work at Venus, I don't know.
It gets pretty turbulent pretty quick, so Last one, I'm just noticing, just going to mark Phil doesn't like my Apollo cache idea. My last one is, the question of, actually I can throw the slide back up. So the arrow, the question mark arrow. It seems like drop them back away and let the sample return lander grab them with an arm. Seems the least challenging, like as a handoff.
Right.
But just thinking about this, as I pretty much whenever you describe anything I think about hasn't been done before, remotely controlling 2 spacecraft that close together. The helicopter and Perseverance. So Ingenuity and Perseverance operated relatively close to one another. And I know that was a concern at first. But we've never had something approach something else. We've had humans approach Surveyor 3, but that's not particularly risky. Could be interesting because the proximity, I mean, it's 22 minutes away in terms of delay, so or more. Could be, I don't know, are there reservations about bringing spacecraft on another planet that close together?
Well, you'd have to be careful. I don't know.
I
don't know exactly. I don't know exactly how they plan to do that. But I suppose the longer the robotic arm on the lander is, the safer that system can be.
I think even with Perseverance and Ingenuity, if I recall correctly, Perseverance drove like 100 meters away because there was concern, like, what if it takes off and just smashes into the rover?
Right.
Yeah, it did. That's right. Yeah.
With something like this, maybe it's something where you can implement like vision system kind of stuff where it like automatically identifies where the tubes are, because it should be very easy to say like tube versus ground that is not. It's probably something where like it wouldn't actually be that difficult to do. And I mean, we have some experience with this with like, the arms on like Curiosity and Perseverance, like drilling samples and then delivering it into itself into
That's
like the ovens and whatnot. So I think it'd just be very similar to that.
Yeah, right.
And I guess some of the smaller rovers driving off of their landing platforms, like Sojourner and Lunacat even. I mean, it's technically 2 spacecraft operating on top of each other.
Yeah.
All right. I think that's about wraps it up.
Okay, great.
Yeah, thanks so much, Phil. So on the spot, if we all had to guess, when will Earth have pristine Mars samples? Phil, you go first. What year?
Well, I think it's quite likely that we could have Chinese samples in about 2032.
Okay.
I was going to say 2035, so very similar.
Okay, and ever the pessimistic, I guess. For first, I'll go 2040. No, that seems so far though. Yeah.
I mean, the real question is, will we get samples back before a human goes to Mars?
Yeah.
I would wager yes. Although, you could have. I don't know if the technology would be the. I think if you had competing human spaceflight versus sample return programs, and you have them competing for attention and money, that would one of them's going to lose, and I think we both know which one. Technology, yeah. Technology wise, sample return should be way sooner, but
well, yeah. I mean, I suppose you could even consider a possibility. I don't know how well this would work, where a first starship landing on Mars happens to be right next door to the Perseverance cache, and they collect the samples and bring them back. I don't know. I'm not very confident in that.
Well, that's where I feel like a discussion of like cost benefit analysis really can come in. It's like if we're spending, before $11 billion to send back, I think it was like 4 kilograms worth of rocks. Is that worth $11 billion as opposed to if we put that 11 billion toward a different mission, or even like towards sending humans to Mars to be able to do sample collection, or something like Starship that can bring a lot of lab equipment there, so you don't have to necessarily bring those samples back to Earth, at least not right away. Like when the numbers are that big in terms of the budget, I feel like those questions start to come up. If you have something like the Rocket Lab solution where you're talking like $2 to $4 billion, then you're back in the realm of like, we're never going to be able to send a mission with humans for that cheap. No. So maybe this does start to make sense. And you're getting that extra infrastructure like the communication satellite.
Yeah.
Yeah, I mean, the price on humans to Mars is going to be, there's going to be some sticker shock, I think. And I'm sure there's already numbers out there, but there's been numbers out there since the 80s. Yeah, we shall see. We shall see. So again, thank you so much, Phil. Thanks, Tanya, for joining. Thanks, everyone, for watching.